Hello, my name is Morgan Nelson, and today we are going to be learning about Bogosort. Bogosort is a sorting algorithm that continuously generates random permutations of a given list until the sorted output is generated. It takes in a given list of n integers and outputs that list in sorted order. This algorithm consists of two steps: the check operation, denoted in orange, and the shuffle operation, displayed in mint green. The check operation is going to check if the given input is sorted. If it is not, the list will be sent to the shuffle operation where a new random permutation will be generated. This new permutation will then be sent back to step 1. This process continues until the sorted permutation is produced on the nth shuffle. Note that in this case, it only took 3 shuffles to produce the sorted output, but the value of m varies each time that the algorithm runs, as it cannot be known how many random shuffles will be performed to achieve the sorted output. Now that we have seen how the algorithm works, let's analyze the runtime per operation so we can better understand the time complexity of Bogosort later. We will begin with the check operation. When the input is entered into the algorithm, it is stored as an array. The check operation begins at the first index of the array and compares the integer at the current index with the integer in the next index. Assuming that the list is being sorted in ascending order, if the current index is not less than or equal to the next index, the check function will conclude and send the list to the shuffle operation. If the list is sorted, the check operation will go through the entire list until it reaches the last index. Since the check operation either stops once it finds 2 unsorted integers or goes down the entire sorted list, this operation runs in linear time. Now, let's analyze the shuffle operation. It starts at the very first index in the list and swaps that index's integer value with another random element in the list. Once the swap is performed, the shuffle pointer increments and the next index in the list is selected and randomly swapped. These steps are repeated until the shuffle pointer reaches the end of the list and the new permutation is generated. Since this operation increments through the entire list and ends once the end of the list is reached, it also runs in linear time. By knowing the runtimes of both the check and shuffle operations, we can now understand the runtime complexities of Bogosort. In the best case, the input list will already be sorted. When given a sorted list, the algorithm will conclude right after the first check operation. Therefore, with only 1 check and 0 shuffles, the best case time complexity for Bogosort is big O of n. In the average case, all possible permutations of a given list will be generated by the shuffle before the sorted permutation is achieved. Note that for any given list with n distinct elements, there are n factorial possible permutations. So, a given input of 3 integers has 6 possible permutations that the shuffle could generate. Thus, for a list of n unique elements, there is expected to be n factorial checks and n factorial shuffles, giving Bogosort an average time complexity of big O of n times n factorial. In the worst case, notice that m is unbounded. Recall that the number of m shuffles that a given input will require to produce the sorted output is unknown. So, in theory, and in very unlikely circumstances, the sorted output may never be generated by a shuffle. This means that there will be an unbounded number of checks and an unbounded number of shuffles, resulting in a worst-case runtime complexity of big O of infinity. It is important to include that while big O of infinity is the worst-case time complexity for Bogosort, the infinite monkey theorem states that after a certain period of time, Bogosort will generate the sorted output. The following tables recap the runtime complexities of Bogosort that we just learned. But what is the space complexity? We know that Bogosort takes in an input list of size n. Throughout the entire algorithm, the list is only checked and shuffled where its size n remains unchanged. Thus, the space complexity of Bogosort would be big O of n. However, some analyze space complexity by calculating the extra space that the algorithm requires, not including the size of the original input. From that perspective, Bogosort would have a space complexity that is constant. Bogosort is deemed as extremely inefficient due to having n factorial in its average time complexity. Let's see why n factorial causes such a big issue. As we previously learned, for any list of n distinct integers, there are n factorial possible permutations. Therefore, a list of 2 integers would have 4 possible permutations. Doubling the size of the list to size of 4, there are 24 possible permutations. A list of size 8 would have 40,320 permutations. And finally, a list of size 16 would have over 20 trillion possible permutations. This is Bogosort's downfall. As n slightly increases, the number of possible permutations increases exponentially. This causes Bogosort to perform extremely slowly even when n is not that large. So, what is Bogosort used for? Due to its inefficient time complexity, Bogosort is commonly used in an educational setting to demonstrate why the time complexity of an algorithm matters. It displays that even if an algorithm achieves its desired output, it is not useful if it takes forever to do so. In comparison, sorting algorithms like merge sort, insertion sort, and bubble sort are all more efficient. And that is Bogosort. Thank you for watching.